Good evening, everyone. Can you hear me? If yes, can you please give me a thumbs up in the chat or here, whatever? Can anyone let me know I'm audible clearly? Like, is my voice clear? Okay, okay, okay. So this week we have, I think I have not shared the screen right now. Okay, can you see my screen? I hope you can see my screen, right? Okay, okay. Uh, okay. So this week we have gone through this uh, module module for this week number 4. So we have discussed linear algebra in MATLAB. So basics of linear algebra. So uh, we have reviewed a lot of things like what is a vector and what is the rank and what is how do we find the solution of a linear system of equations. So so these are some examples like if you have two uh, uh, you have a system of two linear equations, then you can also plot it like this in MATLAB. Like you have basically you have two lines. Like if you have a two cross two system, it means basically each each equation is a each equation represents a line in a Cartesian coordinate system. So if you uh, plot these two lines and if they are intersecting at some point, it means that system of linear equations have a solution. And if they don't intersect and they are like this parallel to each other, it means that they don't have any solution. It's like uh, you can say they are like or linearly dependent and they don't have a solution. And in this case, third case, you can see that these two lines are exactly coinciding with uh, each one. So this system is also linearly dependent, but with infinite solution. Here there are no solutions. So so these things like you can like whenever you see like because this is a simple case like for a two cross two system, you can plot it and see that if there is a solution or if like or if there are no solutions or if there is like if there are infinite number of solutions, you can plot and see. But as the dimensions become larger, let's say if you have a three cross three system, then whatever the equations you get, those are like basically planes. So like maybe you can plot them and you can see if all the planes like you will get three equations and you can plot all these three equations and you can see if all the planes intersect at a certain point, then you can say that okay, uh, this system has a equation. But if you have a four cross four solution, it means uh, like you have to take four dimensions. It is not possible to imagine four dimensions. So you cannot do just by plotting. You cannot probably uh, do this calculation and find out the solution of linear systems just by plotting. You have to have some kind of techniques through which you can find out the solution. So that's what linear algebra does to us. Like there are a lot of techniques by taking the matrix systems and its properties, we can do a lot of computations and find out the solution of linear system of equations. So sometimes, like it is possible to find the exact solution, like uh, like basically doing it uh, like you can do a one shot solution. Sometimes you have to go for the iterative techniques, like as discussed in this uh, as discussed in these modules, like the Gauss-Seidel method or the Jacobi method. So you can use these techniques to find out solution of linear system of equations more efficiently. So what happens is, like let's say if you have a 100 cross 100 matrix, or if you have a 1000 cross 1000 matrix, so then if you want if you want to do the inverse of that matrix, it becomes very computationally inefficient for the computer to find out the inverse. So then there are lot of techniques which you can take to avoid this inefficiency, like Gauss elimination or LU decomposition, or like there are a lot of techniques by which you can avoid like doing the inverse and finding out the solutions in a more efficient way. So that's why we have we are using different methods in these modules. Like maybe you cannot appreciate it right now. Uh, I think during the course, as we go delve into like the modules which we are going to see in the coming weeks, then you might be able to appreciate a lot of these things which we have learned in this module. Okay, so first thing is the condition number. So we have seen that this system of equations, like 1, 2, and 3.999, has these two eigenvalues. Like lambda 1 is minus 2 into 10 to the power of minus 4, and lambda 2 is 4.99. So the thing is, like condition number is nothing but the ratio of absolute maximum eigenvalue, absolute maximum eigenvalue, divided by the absolute minimum eigenvalue. So if you do the ratio, you can get the condition number of a matrix. If this condition number is very high, then your system will become very unstable, and you can get the solutions even for smaller, as you can see on the right side. If I have 2.001, I am getting this solution. As soon as I change this value for the same system, you can see that the solution is like going uh, like it's diverging very heavily. So this is because you can see that it is basically these two systems are basically very linearly dependent systems. Like you can see it is 1 2, and if I multiply this system first equation with 2, you can see 2x into 4y. So 4 is like very near to 3.99999. So linearly, like they are like very linearly very close to being linearly dependent. That's why we are getting a very high condition number. So if you can if you want to let's say, I think I have yeah. So whatever the uh, I think no, yeah, please. So this is the same thing which I have plotted. Like you don't worry about the sims and all. Like it's just I'm using symbolic computations, like declaring symbolic variables and all. I think we will learn this as we go into future modules of this course. So I'll plot this, and I am also uh, like finding out the solution of this two equations. Let's say if I do this, I'll also add here PLC and clear so that I don't end up. Okay. So I'm getting solution 10, and you can see that this is my plot. So basically, this blue line, and I also have this red line for this system, x plus 2y is equals to 1. But these are like very like almost coinciding lines. So that's why you cannot see this. They are parallel and like coinciding lines. So that's why you cannot see this uh, red line. So blue line is over dominating. The color blue is like over dominating. That's why you cannot see it. Okay. So here you are getting solution as 10. See, like if I just make it 2.001, I'm getting the solution as 3 and minus 1. So same thing, like these two lines, by like if you have two nearly parallel lines, and if you just like uh, move one line like a little bit, uh, then your solution can like diverge very much. So that's why this thing happens when your system of equations are like nearly linearly dependent, like columns of your coefficient matrix are linearly dependent, then your condition number becomes very high. So here the condition number is uh, what do you have? We have the uh, equation one and equation two. Let's say I'll give A as 1, 2, and this is 2, comma 3.00, 3.9, and 1, and I'll check the condition number. So I'm getting like you can see this is almost 25,000 uh, condition. So high condition number is not like very good for us. So we always try to uh, make or find out matrices which have like low condition number, because high condition number will lead to instability, lot of instability, and finding out the solution will be like very difficult. So that's why condition number plays a very important role. Like you can just also find out the eigenvalues also, like I. So if you use I, you can see. So this is first eigenvalue is 0.002, and this is uh, 4.992. As I have said, if you do this absolute value of uh, the second eigenvalue, which is the largest, and the first eigenvalue, which is the smallest, I can get this. So that's how condition number is calculated. You find out the eigenvalues and you can uh, get the maximum and minimum, and absolute values of those are divided. Then you can get the condition. So we have this lot of uh, uh, operations like commands which we can use like whenever it is required. So like LU decomposition, norm is nothing but like finding out the magnitude of a vector, like, or you can say distance of the vector. So, and we have seen like we can use this uh, inverse or A backslash uh, B. Both of these we can use to find out the solution of any linear equation, any linear system of equation. So MATLAB encourages you to use this A backslash B instead of using this like X inverse A. Like if you just see here, if I have let's say B also. Uh, okay, I'll just say I have B 2.2 comma 3.9 and B is equals to 1 comma 2.01 and I want solution, let's say X is equal to inverse of A into B. So you can see that inverse of A into B can be slower and less accurate than A slash B. Consider using A slash backslash B for inverse of A into B. Uh, or B, if you have like B into A inverse A, you can use the B forward slash A. So this is some computational inefficiency which occurs if you use the inverse function because like they have written the functions which favor this kind of scripting. So that's why we will use this. But otherwise, like you will get the solution, but it's like if you are like solving large systems, this will give you faster solution, and the other will give maybe slower solution. So like, yeah, sorry, I'll just run this minus. Yeah. So right, like this, we can find out whatever the solution which we want using this uh, inverse into it directly using like uh, MATLAB's functions. So the other thing which if you want to avoid like doing the inverses, which we can do as we can as I've told like sometimes it becomes very challenging to calculate the inverse of a matrix. So then we can go for these numerical methods. So the first one which we have gone through in this course is the cross elimination method. So in this, what we do is like we create an augmented matrix. So we already have like A and B like from the setup of the problem. Like A is the question matrix and B is the uh, matrix of this right hand side. So I'll add this matrix B as a another column to the existing A matrix and I'll create an augmented matrix. And then after that, I'll try to make an upper triangular matrix. So I just like if you go what is an upper triangular matrix is like we will try to uh, make the all the elements which are below the diagonal principal diagonal to be zero, then that is called as a upper triangular matrix. So we have this code which we have discussed in this uh, module, like the exact code which was taught by Professor Niket. So let's say if I run this, I am getting the solution like which is 1, 2, 1. Like I can just also use like let's say if I am doing A backslash B, also I'll get the same solution. But I'm using Gauss elimination here. So what I'm doing is like I'm first taking I'm giving this input A and B, both the matrices. One is a matrix and one is a vector, and I am creating the augmented matrix. just by adding B is another row, and then I am what I am doing is like I am trying to make all the uh, sub-diagonal elements which are below the diagonal, principal diagonal, uh, to be zero. So we have the pivots. Like first, I'll take the uh, first element of the first row and use it to make the first element of the second row and the first element of the third row to uh, to make it zero. So here for that, what I have to do, I have to get this alpha value, which is basically uh, the let's say it is the we are first trying to nullify the second element, first element of the second row. So that divided by the first element of the first row, and if I multiply this alpha with the first element of the first row, I'm basically I'll basically get this uh, all the row elements which let's say if you have where is it? So like if I have let's say matrix 1 1 1 2 1 3 3 4 minus 2. So I'll take this first row and multiply it by 2 and subtract it from this uh, row. That will give me the modified second row, and then like you will get 0, and then what I'll do is I'll take this first row and multiply it with 3 and subtract it from all the elements of the third row. So that will make my first element in the second row and the first element in the third row to become 0. So that is what this alpha is doing. It's not like uh, thing difficult things to do. So you might have all learned this uh, in your graduation. So then we will do the back substitution because like we like after doing the after after eliminating the first element of the second row and the third element of the first element of the third row to be zero, then we have to go for the second column, uh, and we have to see that whatever the elements in the second row, what in the second column below the second row are there, they should all be zero. So we will do the same thing. Like we have this system. So we have, let's say we have this only. So we will take this and we will multiply it so that this, we will multiply it to this and this uh, with something so that these two things become the same. So let's say if I multiply this second row with 3 and the third row with 2, whatever I get, uh, I'll subtract the second row from the third row. You will get this second term to be 0. Then what I'll take this and again this I have to make it 6. This second element in this fourth row, I have to make it 0. So for that, I have to take this row and multiply it with something so that it becomes equal to this. So what I can do, I can multiply it with 3. It becomes like entire row I have to multiply it with 3 and subtract it from here. So this will make whatever the modifications, and then we can like similarly if if here, because this is a 4 cross 4 system, again I have to uh, make again I have to make this also 0. So I have to take this and take this row and do some kind of row operations so that this element should become zero. So that is what we do in Gauss elimination. And after that, what we get is like all these elements 2, 1, 2, 3, 6, 5. These elements below the diagonal will become zero. And then after that, we do the back substitution. First, we will get the x4 value like 8x4 is equals to like you can take x4 is equals to 4 by 8. You will get zero point 0.5. Then you will substitute x4 in this, and using that you can get x3, and then you can get x2, and then you can get x1. So that is what back substitution does. So that's how we solved everything which we have seen using the Gauss elimination. So so like a very efficient way. So like initially, because we don't know, I just want to declare the variable x, so I'm just assuming it initially as zero, and then like I have done this like for like doing the back substitution from last, like first I'll find out x3, and then I'll find out x2, and then I'll find out x1. So it's like we have seen in this uh, module, like not a very complicated, just we have run for loop here so that it becomes efficient. Like I won't have to write multiple lines of codes. Instead of that, I'll just run a for loop. So that will make my code like less clumsy. So it will take care of everything from x3, x2, and x1. So, and then if I run it, I'll get this solution like 1 to 1. So that's what Gauss elimination does. So Gauss elimination, like uh, this is the thing like back substitution, like So uh, let's say I think you have understood it. Like if anybody has any questions in Gauss elimination, you can please ask me. I'll clarify it here and now. Like uh, because we can move forward without any confusions. So if you have any doubts in Gauss elimination, you can ask. I think it was clear. Like if you have any doubts in the method or in the code which was written, please unmute and answer. You can also ask in the chat box. Okay, I think that was uh, that was understood by everyone. So next, we will go to the other lecture in this module, which had this LU decomposition and partial pivoting. So LU decomposition basically we do it because like uh, it is like if you want to, let's say if you want to find out solution for a linear system of equations in which, let's say, if this b vector is changing, like the values of 4, 7, and 9 are changing, and you have to, like, let's say, as this b vector changes, all the other things are like the coefficient matrix will remain same, but this b vector is like changing again and again. Then it becomes efficient to do the LU decomposition and find out the uh, solution. In this module, it was only like LU decomposition was only discussed like up to like we are just doing the decomposition. Like we have already seen that in the Gauss elimination method, whatever the matrix which we get is the upper triangular matrix. So the U is already like derived. Like in Gauss elimination, you can get it, and like only we have to get L. So L is nothing but like all the principal diagonal elements are 1, and then whatever the alphas which you are getting, so those you have to substitute below the diagonal and you'll get the L. So basically A is equals to L into U. So, and this up to this only we have like discussed, like if you want to learn more about uh, I think getting mm, getting the solution of a linear system of equations by like doing this LU decomposition. Like you can go to this computational techniques course taught by Niket only. So in that you can find more details. Also, after this class, I will upload the material for this session, like in the link which you can access through my the group Google Drive link which I have shared in the Google Sheets. So I'll upload a text for computational methods in engineering, I guess. So that is a textbook by Professor S.P. Venkatesh, who was a faculty uh, at IIT Madras. Like he is retired right now. But when we took the course for computational methods in engineering, we used to refer the book. It's a very good book. Like it has all these things. Mostly whatever uh, the concepts which are taught in this course, you can find a lot of uh, examples or like a very clear explanation to the concepts you can find in that book. I'll make sure that I'll upload it after today's class. So you can refer to that textbook and you can learn in more detail if you want to learn more about this LU decomposition or the other techniques, like what is partial pivoting on this. So, so then we have also seen partial pivoting, like in Gauss elimination, along with just like doing Gauss elimination. So sometimes it becomes efficient to do this partial pivoting. Like partial pivoting is nothing but like you ensure like to exchange the rows so that the pivot element is nothing but like if you have the first row, then in the first row, the first element with the pivot element. In the second row, the second element is pivot element. So we want to make sure that in a particular column, the pivot element is the largest. So it ensures computational stability while we do this computational techniques. So sometimes if you don't have this, if you don't do partial pivoting, your solutions might diverge and you can get some abrupt solutions. So for computational efficiency, so we are going to use loss elimination along with partial pivoting. So there is also like complete pivoting and all these things. Like you can also uh, check in the text which I'll share, like partial pivoting and all these things. So we have also, uh, let's say, I think, yeah, partial pivoting. So in this is the same code for loss elimination. I have just, we are just doing this uh, swapping of uh, rows so that our uh, pivot element is the largest in that column. So we will take first, like we will give the input and then we'll get the augmented matrix. And then after that, we will take the first column and check in that first column which element has the highest value, which is the maximum value. And we will get the index of that uh, maximum value. And if I get the index, it means like, let's say if I get uh, index 2, it means that in the second row, in column 1, I have the uh, uh, maximum element value. So what I'll do is I'll exchange second row with the first row. So using this index, I'll use this swapping of rows. Like you can, of course, I think if you have done some kind of programming course, you might have learned about swapping of numbers using a dummy variable. So here also we are doing the same thing. We'll take this dummy as a dummy variable, and and the first row I am replacing it. I am exchanging the first row with the row which has the highest value, and then I'll uh, exchange that row with the first row. So that's how we will exchange. So then I have to do this like uh, calculation so that I have to make the uh, s- uh, second element in the first column and the third element in the first column as zeros. Then I have to go for the other rows also so that in the second row, second element should be maximum. In the second column, the uh, pivot element, which is the second element, should be maximum. So again, I'll do this. Here you can see that like in the course, this one, like in the lecture in which it was in this thing was taught, partial pivoting was taught. There was a small error that first we are trying to like first row is exchanged and first row is fixed now. So we don't go for the first row. So so what we have to do is in the well while we take column 2 to find out the pivot, we will ignore the first element and we will go from the second element to the end. Okay. So and then we will find out the maximum value and we will get its index. And then I'll take a dummy and I'll store the second row in that dummy variable. And then I have to exchange the second row with the row which has the maximum uh, pivot value. So here you can see that here we have just used IDX. Here we have to additionally add IDX plus 1. So because you can see that I have neglected the first row in the second column because first row is fixed. But when I want to swap it, I have to make sure that the index value should like should be corresponding to the augmented matrix which I have. So that's why we have to add this plus one. So otherwise, if you don't add this plus one, the calculations will be wrong. So there was this was the error in the uh, course module lecture 4.3 which was taught like in partial pivoting. This was a slight error. So if you have like used this code or if you have like written, so I was writing this code and I got the doubt, and so and then I have just modified it. So make sure like if you are using this if that if you are using that code, so you have to make this modification. You have to add plus one here. So and and also like there was one thing like here professor had taken this value also as dummy, but it's like there will be a lot of confusion if you take dummy like the variable name dummy here and also dummy here. So I'm just using this symbol. So like this is like because I'm not using the maximum value of column one. So I'll just take this like symbol to store the value of column one, like maximum value of column one. Because like if I'm assigning the maximum value of column one to dummy and again I am assigning the first row to the dummy, it becomes like confusing. So I'm just using this symbol. Okay. So whenever you want to get some output but you don't want to use it, then you can use this like symbol. So like similarly or whatever, I don't know the exact name of the symbol, you can use it. So like to avoid confusion, I have used this symbol and there was like slight error here. So which I have fixed. So because we are going from like in the second row, we are neglecting the first row because first row is already modified, no change. So you have to check from the second, third, fourth, fifth, whatever all these things are there. In that, you have to get the maximum value and you have to swap that row with the second row. And if the second row is swapped, then you go for the third row. And you go for the third column, and in that you will like, again ignore the first and second rows, and and you will see from third row to let's say nth row, you will see, and in that whatever there is maximum, whatever has the maximum pivot value will exchange. So this will go on. So till we do this partial pivoting, like this will go on, and after doing that partial pivoting, like we can get the same, like we will do the same thing whatever we have done in Gauss elimination, and we can get the solution. So I'll just also add here CLC and here. I run it same. Again we'll get the same solution. So this is how we do the partial pivoting to enhance the computational efficiency of our Gauss elimination method, or rather, I'll just does anyone have any doubts in this? You can unmute and ask. Everything is fine. Okay, I think you have understood. Okay. If you have any doubts, I thought I'll join the iPad and explain because it's cannot write here. Let's and just give us slight example. So you can see, right? You can see here, right? This. So while we do the back substitution, you can see that we are dividing everything like x3. Uh, we are dividing in x2, x3, and also in x1. So you can see that we are dividing the numerator with the pivot element. So here A33 is the pivot element, and here A22 is the pivot element, and A11 is the pivot element. So we are dividing it with pivot element. So if your, let's say, pivot element is like very small, let's say it's like let's say it is zero, it becomes computationally like it will throw like infinity, will you will get an infinity answer. So you will get infinity as answer. So it is not like computationally efficient. Like I don't want infinity to occur. Let's say if your A33 is, let's say, 0.0001. So let's say if I just like due to rounding off, I just, let's say, 0.001. Beyond that there are some decimals. If I even miss like some decimals, if I divide it by a very small number, if I do, I'll get some solution which is not like very stable. Like if one decimal is missed, like for a very small number, you will get a very uh, divergent solution. So we don't want that to happen. That's why we are doing partial pivoting. So that's why we want this pivot elements to be the largest, to be the maximum value in that column. So that's why we are doing partial pivoting. So like in the problem which we have solved, it's like even if you don't do partial pivoting, we are getting the same answer 1, 2, and 1. But if there are some cases where your these pivot elements are like very small, or if they are like zero or near to zero, the solutions will become very unstable, or you will get infinite solution. So in order to avoid that, we do this partial pivoting. Okay, I think that gives enough motivation to why we are doing partial pivoting, right? You want the denominator to be the highest value. If the denominator is very small, then your solution may go near to infinity. Or if you are doing rounding off, like if the denominator is very small, solutions will diverge. Even if you neglect some decimals, you will get some other solutions. Okay. So then we have gone through this numerical methods to solve the linear system of equations. The two methods which we have discussed are the Jacobi method and the Gauss-Seidel method. Jacobi is a very simple method. So in these numerical methods, what we do is we initially assume some solution for our linear system of equations, and then we will find out the solutions iteratively uh, by solving it like numerous times. Like so here in Jacobi, the thing is like if you have a uh, you have assumed some solution. If you have assumed some solution, x1, let's say, uh, like uh, for first iteration, let's say all your like assumed solution is 0, 0, 0. So using that assumed solution, you will find out uh, x1 value, x2 value, x3 value, like up to n. Like if you have a n-dimensional vector for x, let's say if if you want x1, x2, x3 is the solution, like if your vector has x1 and x2 and x3, so you will find out all those values using the initial solution which you have assumed. So that is the Jacobi method. In Gauss-Seidel method, what we do is I'll find out the same thing we are doing, but what I will do is if I have, let's say, if I have assumed x1, x as 0, like all the values of x as 0, then what I'll do is I'll first find out x1 for the first iteration. And after I'll, I find out x1. So in the next step, when I find out x2, I'll also use this uh, x1, which I have found out uh, in this iteration only before the previous step in my calculation. It becomes more like more efficient. So like earlier I was not doing it. I was taking all the elements, all the assumed for all the steps for x1, x2, x3, x4, I was using the previous solution only. But here, as I find out x1, I'll replace x1 with the value of second. Like while I'm calculating x2, I'll use the x1 value, updated x1 value. While I'm calculating x3, I'll use the updated x2 value. So that is the difference between the Gauss-Seidel method and the Jacobi. So it's like Jacobi method is very simple. So like you don't need a lot of you won't be like getting a lot of confusion. So it was also not taught in this module in the lecture. So you can just go out. You can just go and check uh, uh, the computational techniques course. Like if you have any doubts in the Jacobi method, so you can go and check. Or if you want me to explain uh, this, I can explain it right now. So, you have any, do you have any doubts in these two methods? How we are doing it? What is the thing? Of course, we'll go through the codes, but uh, I want you to be very clear with this formula. Okay? Does anyone have any doubt? You can type it in the chat box, or you can unmute and ask me. Okay. Seems like, yeah, anyone has anything you want to ask? Okay. No doubt. Okay, fine. Yeah. So again, you can mm, read the textbook which I'll share in the course materials, or also you can go through this computational techniques course which was taken by Professor only. So in that there are various examples discussed. So the thing with these numerical techniques to find out the solution of linear system of equations is that, so whenever we do these calculations, like iterative calculations, so if our matrix, the coefficient matrix or A matrix is not diagonally dominant, so the convergence will not happen. Like solutions will diverge and you won't get a solution. So when I say divergence, it means like when I say convergence or divergence, it means like as I go on doing the iterations, my solutions should stabilize. Like if my solution is, let's say, 1 1, and I'm starting with 0 and 0, so x vector, I'm assuming like a 2 by 2 system, and if I have a 2 by 2 system and I'm assuming the solution vector as 0 and 0, and I'm doing this iterative calculations using the Gauss-Seidel method. So I know that, like, let's say in this case, I know that my solution which I have to get, the true solution is 1 1. So le- after n iterations, like as I will do, like, let's say 5 or 6 iterations, this solution should stabilize. Like it should come near to 1 1 1. Let's say it will come to 1.2, 1.2, and then it will come to 1.1, 1.1, and then in the next iteration, it should come to 1.05, and then, like, let's say after 10 iterations, it should come very near to 1. So that's what convergence means. Like if I calculate the error, when I say error here, it's the difference between the uh, solution in the previous iteration and this iteration. It should be, it should be, uh, it should become very, very low as I go on doing the iterations. So if this error is like increasing, it means my solution is diverging. So it is not a good thing to happen while you are doing some iterative procedure. So I think next week we are going to learn about nonlinear equations, solving nonlinear equations. There, these iterative techniques are like are the only way. Like mostly, you will be using everywhere. Like while solving nonlinear system of equations, we have to uh, go to some kind of iterative technique to get the solution. So there, like convergence, as I said, in iterative methods should be a top criteria. So if your solution is diverging, then the algorithm which we are using is like not suitable for the problem. You might want to change it, or there is uh, some discrepancy in the input which you are giving. So that's why we have to make sure, like in this case, for linear system of equations, this Gauss-Seidel methods or will converge, or Gauss-Seidel or the Jacobi methods will converge mostly in the cases where the matrices, quotient matrices are diagonally dominant. So here you can see that this is the system x1 plus 2x2 is equals to 1 and x1 minus x2 is equals to 4 and x1 same, like I am taking the uh, same system of equations, but I'll initially take this as my first equation and I'll find out x1, and then I'll take this as the second equation and I'll find out x2. So the thing which we have seen like in the course already is that if I do this iterative procedure using the Gauss elimination method, Gauss Seidel method, we saw that the solution was diverging. Like uh, it was not like we were not getting the solution converged, or there was not a stable solution. Like error was increasing as I was like as we were doing it. That was because like you can see that this is a uh, if I take let's say I just try to MATLAB 1 2 and 1 minus 1. So this is my A matrix, 1 2 and 1 and minus 1, and our B was 1 and 4. I'll just run this and just print here. So now you can see that this in the first uh, in the uh, first column, you can see that like we have 1 and 1. So like you can say like I cannot change anything about this column. So in the principal diagonal, now you can see in the second column, in the second element of the principal diagonal, you can see that if I exchange this 2 with minus 1, my principal diagonal dominance will increase. So that's why if I swap this 1, 2 with 1 and minus 1, like if I exchange the rows, so then my principal diagonal will become more dominant, and then that will lead to a more stable solution. So like it will give you convergence. So that's why diagonal dominance is a you can say a sufficient condition, not a necessary condition. Like sometimes you might get solution even though if you don't have diagonal dominance. Uh, the thing is like uh, this example was discussed in the class in the module, which in which professor has told us like you just uh, rearrange two equation three, like you take equation two as the first equation and three as the second equation and one as the third equation, and you solve it. And we see, let's, where is that? Yeah. Um, so if I solve it, if you can see that as I was solving it, my error was like uh, getting reduced and reduced and reduced. So I have like done this for 25 iterations. Like I can also put a, uh tolerance criteria here. Like if I, let's say if my error is becoming below some threshold, I can just say MATLAB to break out of the loop and give me the solution, whatever it is there. So that also I can do. Like instead of like doing the uh, doing lot like some unnecessarily doing lot of iterations. I can stop it somewhere below some convergence criteria. Like if I'm, let's say if my error is going below this value, I can say, okay, get out of this loop and give me the solution. So let's say I think I have this X25 this is just X. So this was my solution. Now you can see that we know that this system which we have solved using the Gauss elimination and also uh, this Gauss elimination with partial pivoting. We have got this like, and also we have used like x is equals to a inverse b. Like directly we have solved using the inverse of matrix here. So you want to show how to? Okay. So what I can do is, one thing I can do is I'll just like this. Here I can write. I can also tell x equal to this thing. Say str. Yes. So then here I have, say how we should do. Just run it. Or I can do just remove this. This format is something wrong. I can just say display. So you can see that every iteration, after every iteration, or let's say I'll print this below this. So I'll run. So you can see after every iteration, you are basically getting also the solution vector. So this is the first iteration and this is the error and this is the solution. And this is the second iteration. This is the error and this is the solution. You can see that initially we are starting with uh, initially we have assumed it to be zero, and then after the first iteration you will get this solution. Then After the second, you will get this. Third iteration, you'll get this. So slowly, 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 we are going uh, iteration by iteration. We are doing this, and we are getting closer and closer, closer, and to the true solution. And that's why we can also see that our error is also getting reduced. Like it's like 10 to 2.89 into 10 to the power of minus 1. So we have come very near. Like we know 1, 2, and 1 is our true solution, and we have come very near to it. So it's like there is slight error, but it cannot, like it can be neglected, right? Like it's not a, sometimes like if you don't want to go like you don't want to compute a lot of, let's say in this course only, like if you are just solving some problem, like you don't want like very accurate, like to very lot of decimals. You don't need a very accurate solution, so you can just stop it somewhere. So that's what, like whenever we use numerical techniques, some kind of numerical techniques, we have some tolerance. Like if my error is going uh, say below this, I'll just stop it because I like, because this otherwise these iterative techniques will, like you can run for infinite number of estimations. You will go more closer, more closer, more closer. So it's like not necessary to do that. Like so it will be going on. So instead of that, we can say we can stop at some number of iterations, or we can say like here I'm stopping it at 25 iteration. Or I can say, okay, MATLAB, if you get error below this value, you stop this and break out of the loop and give the solution. So this is what we have done here. So, but the thing is like this matrix which we get here is not diagonally dominant. I don't, because like we have, like the professor told in the class, like you just uh, rearrange 2, 3, and 1, but it is giving a solution, but this is not a diagonally dominant uh, solution. So diagonally dominant is like just condition for diagonal dominant. Yeah, yeah. It's not diagonally dominant even after rearranging. So that's why I was saying that that is a uh, sufficient condition. It's not a necessary condition uh, to like. It's not a necessary condition that like like only if you have a diagonally dominant matrix, you will get you will get the solution. But it is a sufficient conditions. Like it is like it is more likely to have a diagonally dominant matrix. Like if you have a diagonally dominant matrix, then you will sure shot you will get a stable solution. But if you don't have it, sometimes you might get, as in this case, which we have, as in this case, we have seen. So this is not a diagonally dominant matrix. Even if you rearrange the elements, if you even if you rearrange the rows, it is not a diagonally dominant. But like just by like rearranging, it is like you can say uh, trial and error. You can get a solution, but most of the times you won't get it. Someone wants to speak, uh, Dinesh. Oh, okay.
Sorry, sir. Sorry, sir.
You have any question? You can also type in the chat box, or you can unmute and ask. So the thing is, the condition for diagonally dominant. I'll do one thing. See, the diagonally dominant matrix, like condition is like you take the principal diagonal element do the um, like like get the absolute value of it, and it should be greater than some of the other elements which are not in the principal diagonal. Okay. Similarly, this is for the first row. So here greater than or equal to. Okay. So it should be greater than or equal to the sum of other elements in that row. When I go to the second row, this is my principal diagonal element, which is A22. The absolute value of it should be greater than or equal to sum of absolute values of the other elements in that row. So if this condition is met, if this condition is satisfied, then I can say, like here you can see that this condition is satisfied for all the rows. So 3 is greater than or equal to 3, and here also 3 is greater than or equal to 3, and here 4 is greater than or equal to 3. So this is a diagonally dominant matrix, and it will give me a stable solution no matter what. But uh, in this case, let's say if I'll just print A. So you can see that if I take uh, the principal diagonal element, absolute value of it, and some of the other two uh, elements in this row, then I'll get 1 is less than or equal to 2. So that's why this is not a diagonally dominant matrix. If I go to the second row here, you can see that 1 is not uh, greater than or equal to 2 plus 3. So it is less than 2 plus 3. So that's why this is not a diagonally dominant matrix. So here, what we are doing is we are rearranging it. Let's say if I rearrange, and after rearranging what we get AF, right? So forget about this, okay? Forget about the last column. Here you can see that this is the, like after rearranging, like I'm taking the second row as the first row after rearranging, you can see that 2 is not greater than 1 plus 3. So this is not a diagonal dominant. And similarly here, 4 is not greater than 3 plus 2, right? So this is not like a diagonally dominant matrix, but somehow we are getting the solution, because you might get, but like not every time your fate will turn out like this, and you will get the solution. So that's why there are like lot of other things which we have to learn, which are not taught in this module. Maybe you won't get, I think maybe you won't, um, like we won't learn this, we won't learn those things in this course also, might be, I don't know. So like, so that's why, if let's say if you are not getting some convergence, means like there is some uh, condition which is not getting satisfied. So some some other things you have to get, like what I forgot. I what was the SOR, some technique is there. Just give me a minute. I wrote the method. Hope I have this. in my drive. Yeah. It is. Yeah. So this was the text which I was talking about. So I'll upload it. Okay. So this was written by Professor S.P. Venkatesan. So he was a faculty member, mechanical engineering department. Right around that. So if you go through this book, so we have a lot of preliminaries. This also has MATLAB codes. So you can check when these are uploaded. So you can see that programming in MATLAB, everything is given here, like a lot of things. So functions, arrays, matrices. So introduction to a lot of things is given. Loops, operators, plotting, everything. So here you can see solution of linear system of equation. So we have like this also has like Cramer's rule, uh, like which you might have also like these like basic techniques which you might have learned uh, in your 11th or 12th, I think, Cramer's rule or join four factors, all this. So yeah, yeah. I'll share this in the drive after the class. Okay. So you can go through this. So, so there are a lot of things in this book. So pivoting, partial pivoting, some things. So backward substitution is these all these things are there. Gauss elimination. We have also uh, Gauss. Let's open this. Okay. We do have Gauss Seidel also. So there are also these tridiagonal things. So you can see that uh, here in iterative methods, before doing the calculations, before we are solving it, so we have to precondition the matrix in such a way that we will get a stable solution. So that's where like we can also get this we can like lot of different techniques are there. Like you can do this L plus D plus U. Like you can read about it. I'll share the book. So like L is the lower triangular, D is a diagonal matrix, and then U is an upper triangular matrix. So that's what precondition is. Like uh, you can like basically divide it into like it's like similar to pivoting which we do in Gauss elimination, right? Like partial pivoting, what we have done. So precondition, some kind of preconditioning you have to do. Like this might be one like there might be other ways also which can be used for preconditioning. Like here, this uh, A is written as L plus T plus U. So preconditioning is done to our coefficient matrix or the system of equations which we have. Then we will go for the solution using the Gauss-Seidel method or the Jacobi method, and then we will see if it is converging. If it converges, no, then you have to go and again precondition it and again do the Gauss-Seidel method. And if you if your solution converges, then you can say, okay, this is like error is less than the tolerance, and then you can stop and you can get the solution. If it is not converging, then you have to go and again do the precondition. So some kind of preconditioning we have to do, but in this model we have not seen it. Like if you want to read it, like you can go. Uh, yeah, I'll explain it. Tridiagonal, uh, tridiagonal matrix method. I'll explain it. So I'm just showing it. So we can also do use this uh, SOR technique, which is also there. That can also be used. So like if your matrix is not diagonally dominant, preconditioning is the thing which you have to do so that in the iterative procedure which we are following, we get a stable solution. So I think what is here is that so yeah. So here by trial and error method, we have just basically what I want to say is like we have just exchanged some rows and we are getting the solution because by it's just by luck. Like I can't say anything more. So otherwise, preconditioning is the thing which we have to do, and it was not thought. So while I was solving this, I thought there was something wrong. Then I realized that this was the thing which was missing preconditioning. So I went back to the course which I had taken 2 years ago to realize what was the mistake. Okay. So yeah, Nasir, what question do you have? You want to ask something, Nasir? I can't hear you. I think there is some problem with your microphone. Maybe you can unmute and ask. Sorry, I can't hear you. Maybe you can type in the chat box. Can you hear me? So that was the main limitation of what was taught in the class. That uh, one thing was missing, which was preconditioning and like this iterative methods. I think maybe we'll learn this preconditioning maybe in the next module, I guess. So, because we also use iterative methods there. Maybe some, I have not seen the lectures, maybe I think, because otherwise you won't get a stable solution. So then, so the difference between necessary and sufficient condition is when I say the uh, condition is necessary, it means that it has to be satisfied. Okay. Like otherwise, there is no way you can get the solution. That is the necessary. So necessary means like what if, what are the things necessary in our life? Like basic necessities is like we should have uh, uh, food, clothes, and also like housing. That's what we say basic necessities, right? So otherwise we can't live. So those are the necessary things. Like otherwise you can't live without food, without shelter, or without clothes. So that's what necessary condition means. Like it has to be satisfied. Like there is no way. Like if it is not satisfied, if the necessary condition is not satisfied, uh, you will get a correct solution. When I say the condition is sufficient, it means like if if the condition is satisfied, I'll get the solution. If the condition is satisfied, sure shot I'll get the solution. If the condition is like sometimes it is getting satisfied, even like sometimes if it is not getting satisfied, then also I might get the solution. So that's what sufficient condition means. Like it is sufficient. So it's not like it is a like unnecessary thing. So maybe I'll is it clear? Like whatever the condition, whatever the thing which I have told, I'll just give a better explanation. Can you please just finding a better explanation? Just let's see. We'll ask ChatGPT on this. What is the difference between necessary, sufficient, condition in case of numerical techniques? Give me layman's examples. Let's see what it gives. Yeah. Now you can see the thing which I have told. It has refreshed it in a very better, easier way. That a necessary condition is something that must be true for a method to work, but it alone may not be enough. So necessary condition has to be satisfied, but along with that, some other conditions also might be satisfied. Okay, but it has to be satisfied. A sufficient condition is something that, if true, guarantees the method will work. So if the sufficient condition is satisfied, when I'm saying that my uh, matrix has to be diagonally dominant, if a matrix is diagonally dominant, the method will converge for sure. But it might not be required in all cases. So as we can see that in this course, in this thing here, we have just replaced, like, even though the matrix was not diagonally dominant, it gave us a solution, stable solution. So that's what sufficient condition. If it is satisfied, sure shot, it will give you a solution. Necessary condition is something, uh, it should be satisfied, like, if it should be satisfied for the method to work, like, otherwise you don't have a way out. So diagonally dominance is not a necessary condition, but it is a sufficient condition. So I hope you understood, right? So there are some examples also here. Like, a matrix has to be, like, if you have a linear system, ax is equals to b, the matrix A must be square if we want a unique solution, but just being a square doesn't guarantee us a solution. As we have seen, like, if your A is linearly dependent, we have seen here, right? Where is that? Yeah. So if you want a unique solution, this matrix, the A matrix, should be a square matrix. Otherwise, you won't get a uh, unique solution. So this is a necessary condition. Like, it has to be a square matrix. So necessary condition, like, if you want to get a unique solution, let's say if you want, like, even if this condition is satisfied, necessary condition is satisfied, but if you have, if you have a square matrix in which the rows are linearly dependent, 1, 2, and 2, 4, these rows are linearly dependent, then you can see that these two are parallel lines and you won't have a solution. So there is no solution for this system. Here you have infinite solution. So, but if you want, for sure shot, like, if you want a unique solution, like, you should have a square matrix. So, but that doesn't mean that if your necessary condition is satisfied, it doesn't mean that your so you will get a solution. Like, most of the times you will get, but along with the necessary condition, there should also be some other conditions which might be required. Like, here in this case, the other condition is the other conditions which might be required for getting a unique solution is that the rows of the matrix should be linearly independent. If they are linearly dependent, you will not get a unique solution. So necessary solution is A is a square matrix, but you also need other conditions which should be satisfied. Okay. So that is the necessary condition. And what was it giving? For uh, um, what is it giving? Yeah. If A is invertible, uh, then a unique solution exists. This is enough to ensure that the system is solvable. Okay. So if your A matrix is invertible, like, it has a full rank. Let's say this, right? Where is that? So if your A matrix, this matrix is invertible, for sure you will get a unique solution. In this case, you can see that this matrix uh, is not invertible because this is a linearly dependent. This has linearly dependent rows. Okay, so 1, 2, and 2, 4. This is not invertible, so that's why you won't get it. So sufficient condition is like If this is getting satisfied, if A is invertible, for sure you will get the solution. Okay, that's what. Even if it is not satisfied, in some cases you might get a solution. Like uh, here, not in this particular case, but yeah, sufficient condition is satisfied means you will sure shot you will get a solution. Necessary condition is satisfied means one necessity is like done. Like you will you can get a solution, but subject to some other conditions also. So it is also giving some analogies like you need flour. Without flour, you can't bake a cake. But just having flour alone doesn't mean you will get a cake. So flour is not enough. You have to bake it. You should have other ingredients also. You should have an oven, like all these things. So flour is a necessary condition. So sufficient condition is like if you have all the ingredients in the right quantity and follow the recipe correctly, you are guaranteed to get a. So if everything is done, if everything is perfect, like necessary condition is also satisfied and also the other conditions are also satisfied, it means that sufficient, you have everything in a sufficient manner and you can get a cake. So you will get guaranteed like in a, you will guaranteed like you are guaranteed to get a cake. Let's say uh, if your sufficient condition is, let's say, if you don't uh, uh, you have you have the flour, you have other things, but let's say if you don't have sugar, if you don't have sugar or something, then also you might make a cake, but it won't be tasty. Or like if you don't have cream, you can make a cake which is like a plum cake. You can make a cake. So sufficient condition, if it is satisfied, you will get a sure shot solution. Even if it is not satisfied, sometimes you might get a solution. Necessary condition is like flour should be there. If you don't have flour, you cannot make a cake. So that is necessary. So in the same way here, if you want to get a unique solution, A should be a square matrix. Okay. I think this solves the explanation. Did you get it? Uh, is there any confusion still? That's it. You can type. This is a very confusing thing. I also know, but you can like basically as you go on doing practice, sometimes you will get like full clarity on it. Yeah, Nasik, you can type in the chat box because I cannot hear you. I don't know why. Hope you are typing. That's right. Oh, okay. Okay, okay. Doubt is clear. Okay. So then, after this Gauss-Seidel method, so you don't need to worry about this diagonally dominant thing in the assignments, whatever the questions which were asked. So I think everything satisfies, like you will get a solution. So even if the condition is not satisfied, whatever the questions given in the assignments, so you can solve it. So like as it is, like you don't need to change rows and all. So you if you like you just solve it and you will get the solution. So you don't need to do preconditioning and all. So don't worry about that thing. So then after that, the last lecture in this module was about this tridiagonal matrix. So basically, uh, tridiagonal matrix like algorithm, which was the Thomas algorithm. So for solving these systems which have this tridiagonal matrix, tridiagonal matrix is very useful because like you can see that whenever you have a matrix like this in which the uh, diagonal elements are populated, like you have some value for the diagonal elements and you the subdiagonal and the uh, like and diagonal element of like the one diagonal above the diagonal principal diagonal has elements like u2 u3 here, and also below the diagonal you have some elements, and but these elements which are like far away from the principal diagonal are having zeros, like they are populated with zeros. So whenever we whenever we use our computational techniques, like computational methods or computational techniques, let's say if you are I think mostly mechanical engineer or a civil engineer, so or maybe in electrical also, like whenever you let's say you solve a partial differential equation, you want to solve a partial differential equation, but you can't do it numerically. So what you will resort to is some you won't do it like you can't do it analytically, like you can't get an analytical solution, or it might be very difficult to get an analytical solution. So what we do is we go for some kind of numerical methods like finite element method, finite difference method, uh, or you can say this finite volume method. So lot of different methods which we can use numerically to solve partial differential equation. So one such example which was given is about this heat conduction problem. So this is a ordinary differential equation only, but we are using the central difference formula to get the solution of this system numerically. So we might or we might not be able to solve this. Uh, I think we can solve it because this is a very simple ordinary differential equation. But let's say if you have some very complicated equation for which doing the integration and getting a solution is not possible, so then you can resort uh, to use this central difference formula, or some like you can lot of other techniques are there which you can use and get the solution. So here, so you can see that this central difference formula so will finally lead to the linear system of equations like this. So you will have at x1, x2, x3, like uh, lot of like you will get lot of like let's say if you are dividing it into 10 intervals with gamma is equals to 4, which was given here. So if you are dividing it into 10 intervals, let's say you are going from t. x is equals to 0 to x is equals to 1. Like basically, this is a rod in which heat conduction is happening, and from at one end of the rod, at x is equals to 0, the temperature is 100, and at the other end, uh, at x is equals to 1, the temperature is 25. So basically, heat flows from higher temperature to low temperature, right? So that's what we will see. So here, what I'll do is, so I'll discretize the uh, rod into 10 elements. So from 0 to 0.1, 0.0, 0.1 to 0.2, 0.0, 0.2 to 0.3. So I can discretize into various things. So that's why I'm, like you can see. So that's why I'm getting this T1, T2, and Ti plus 1, Ti, and Ti minus 1. I think we'll go, I think like week 9 or week 10, we'll go more uh, in a detailed way uh, how to do this discretization. I think if it was mentioned. So, or you can, if you want to learn, like you can go to that week's module, or you can go to this computational techniques course and you can see how you'll get. So basically, after discretizing it, you will get this uh, system of equations. So 10, because we have 10 intervals, we'll get some 10 system of equations. And if we solve it, we'll get that uh, 10, like uh, basically 10, like from T1 to T11, like from x is equals to 0 to x is equals to zero point 0.1, x is equals to zero point 0.2, what is the temperature, x is equals to zero point 0.3, what is the temperature. So we can get this like at various points on the bar, I can get the temperature by solving this linear system of equations. So that's what this method is doing. So so if I solve this linear system of equations, I'll get it. Okay. So but the thing is, if I get the coefficient matrix of this uh, system of linear equations, so you can see that there are a lot of zeros in this coefficient matrix. Like away from the principal diagonal, you can see a lot of zeros below and above the principal diagonal. Like just below, like some elements are like populated, like above the principal diagonal, the above diagonal is populated, and below the principal diagonal, the subdiagonal is also populated. But the other things are like all these things are zero. So let's say if I just go and use some kind of like Gauss elimination method, so it becomes like very computationally inefficient. Basically, if you have like some here we are dividing it in 10 intervals. Like let's say if you want temperature of the rod, like 0.001 uh, x is equals to 0.001 also. So you might get like some 100 intervals. So then you will get a matrix which is like very large, and you have lot of zeros in that matrix. So this, like having a lot of zeros uh, is not like a very computationally efficient thing, because these are like, if I have zero, like there is no use of it. So this kind of matrices which have this kind of structures are called sparse matrices. Like if you have a matrix with lot of zeros, you can call it a sparse matrix. So, and also you can say this is a banded matrix, because in the, near the principal diagonal elements it is populated, and away from it, like it has lot of zeros. So for these kind of system of equations, we can use this tridiagonal matrix algorithm, which is the Thomas algorithm, which was discussed. So basically, in that you have to uh, like you have to get this u vector which stores the values of this upper diagonal, and you have to get the d vector. Where is it? I'll just check. So d vector, l vector. So you will just store this. elements of the upper diagonal in a U vector and in a D vector, the principal diagonal elements in a D vector and the subdiagonal elements in a L vector. So you won't store this total A matrix because this has lot of zeros. So if I want to store lot of zeros, it's just a waste of memory. So don't I just don't need to do it. And then after storing it, I can just use the Gauss elimination method, which I have used. Like the same technique I can use and I'll get the solution of the system of equations. What you were using, you were saying was about assignment uh, fourth problem. Let's see. Oh, there is error. Assignment for fourth problem. Um, matrix entries. So there is an error. Understand. Yeah, it's doing it. A54 is alpha. Is I think drop. Matrix, right? A54. Also, yeah, I think there is an error. Okay. It's given. Yeah, I'll do one thing. Uh, uh, maybe I'll just till next Wednesday you have the submission time, right? Am I right? That's the sub deadline is and then it's tomorrow. Okay. So do one thing. Uh, you just take the uh, you just take the correct matrix system. Okay. Whatever here it is given here 0 and 0. It should be alpha and alpha. So you take it, you take the correct system of equations and you do the solution. Whatever the answers which you get, you submit it here. So I'll try to contact with the course team uh, uh, because I don't have like I'm part of the course, but like I'm externally involved. So I'll just mail them and I'll ask them to rectify this mistake. So if there is something, so we'll do it. Okay. So whatever they'll say, if if it is wrong, uh, like the question is wrong and like the time is over, maybe they'll give you the marks. So don't worry. I'll just contact with them and I'll. So I think today we'll end it because I have to go somewhere. I have some work. So if you have some other questions, maybe you can type, you can uh, send it uh, in the Q&A section, or you can also send on your mail. I have already shared with you my email ID. Whatever like doubts which you have regarding the course, or you have any other doubts related to something else, you want something else also. I have put my email ID in the chat box. I have pinned it. So if you want to ask me anything regarding to the session or something else, you can mail me. So I'll try to answer and try to help you. So, otherwise, if you have any doubts, please ask. Otherwise, we can leave. Okay. Nasir, I can't hear you. I don't know why your mic is not audible. You can just pin it here. I'll try to resolve this issue. I'll mail the course team and ask them that there is an error in the thing. Okay, I'll do it.